In this video, we're going to work on some problems associated with electrophilic aromatic substitution reactions. We're also going to work on some synthesis problems as well. And before watching this video, you may want to review which groups are ortho, meta, and para directors, which ones are activated and which ones are deactivated. And there's a video I have on YouTube that goes into that. And if you want to find it, you can access it in my organic chemistry playlist, which is going to be in the description section of this video. So you can take a look at that when you get a chance. But let's get right into it. So let's start with benzene. What's going to happen if we react benzene with, let's say, ethyl chloride using an aluminum chloride catalyst? What's the product of this reaction? Now you need to know that this is the Friedel-Crafts alkylation reaction. And what's going to happen is we're going to replace the hydrogen with the alkyl group. The Cl is going to leave with the Lewis acid catalyst. And so we're going to get ethylbenzene as the product of this reaction. Now, continuing from ethylbenzene, what's going to happen if we react this with, let's say, bromine with iron 3 bromide? What's going to be the product of this reaction? Now, you need to know that the ethyl group is an ortho-para director. So the bromine group can go on the ortho position, which is the same as putting it here, or it can go on the para position. So in this example, we're going to get a mixture of two products. So this is the ortho product. And here we have the para product. Now we're going to get both of these products in good yield. So they both make up the major product. It's a mixture of two products. Now let's move on to our next example. So starting with benzene, what's going to happen if we react it with nitric acid and sulfuric acid? What's going to be the major product in this case? So in this example, we're going to replace a hydrogen atom with an NO2 group. And so the product will be nitrobenzene. So this is the nitration of benzene. Now, starting from nitrobenzene, what's going to be the major product if we react it with Br2 and FeBr3? Now the nitro group, is it an ortho-para director or is it a meta director? The nitro group is a meta director, so it can go, the bromine atom can go there or on the left side. So the left side and the right side will be the same. So we're going to get one final product in this example. And so this is going to be the major product in this example. Now for the next example, we're going to start with benzene and we're going to react it with tert-butyl chloride using aluminum chloride. What's the major product in this reaction? So this is another Friedel-Crafts alkylation reaction. And so we're going to replace a hydrogen atom with a tert-butyl group. So we have tert-butylbenzene as the product. Now, what if we react it again with another tert-butyl chloride? Where is the second tert-butyl group going to go? Now, the tert-butyl group, like any alkyl group, is an ortho-para director. So it can direct it in the ortho position or in the para position. However, due to steric effects, this position is not very accessible, especially for another bulky group. So we should expect the para product to be the major product. So the final product in this example, that is the final major product, is going to look like this. So we want to put the second tert-butyl group in the most accessible position, and that is in a para position. Now let's say if we have a disubstituted benzene derivative. So we have a benzene ring with an NO2 group and an ethyl group. What's going to be the major product if we react it with chlorine and aluminum chloride? So we know we need to add a chlorine atom to the ring. So which hydrogen atom should we replace? Now the ethyl group is an ortho-para director. So the ethyl group wants to basically direct the chlorine atom in the ortho position. The left side is the same as the right side, so let's not worry about the left side, or in a para position, but that's occupied by the NO2 group. So the ethyl group wants the chlorine atom to go here. Now the NO2 group is a meta director, and meta is 1,3. So with respect to NO2, chlorine will prefer to go there due to the NO2 directing it in the meta position. So notice that both groups, they favor this position, and that's where the chlorine is going to go. So when both groups are working together to favor one position over everything else, then this is going to lead to just one major product. And so the chlorine atom will go here. Now let's consider an example where we have a disubstituted benzene derivative, but where the two groups are not working together, rather when they're working against each other. So let's say we have a hydroxyl group and a methyl group that are para with respect to each other. And this time, let's react it with concentrated sulfuric acid with heat. Now, the OH group is an ortho-para director. So it wants the sulfuric acid to go in the ortho position or in a para position, which is occupied. And the methyl group is also an ortho-para director. So it wants basically this group to go in the ortho position. And so these two groups, they're competing with each other. They want the incoming electrophile to go in different locations. So which one is going to win? This is when you need to know what type of groups you're dealing with. The OH group is a strong activator, whereas the methyl group is weakly activating. So when something strong goes against something that's weak, the stuff that's strong is going to win. Therefore, we're going to add the electrophile to this position. So what is the electrophile that we're going to add to the benzene ring? Whenever you react benzene with concentrated sulfuric acid and heat, by the way, that reaction is reversible, but once we use concentrated sulfuric acid, it's going to drive the reaction to the right. It's going to create a sulfonic acid, which you can write as SO3H and just leave it like that. Or if you want to draw it out, you can write it this way. The sulfur has two double bonds to an oxygen atom, and it has an OH group. So we have a benzene sulfonic acid group. Without the OH and the CH3 on the ring, this would be called benzene sulfonic acid. Now let's move on to our next example. And so once again, we're going to have two competing groups, an ethyl group and a methyl group. So which group is going to win? And this time we're going to react it with bromine and with a Lewis acid catalyst, iron 3 bromide. Now, what's going to be the major product in this example? It's important to understand that both groups are alkyl groups. They're both ortho-para directing. And so the ethyl group wants the bromine atom to go in the ortho position, and the methyl group wants the bromine atom to go in the ortho position with respect to itself. Keep in mind, ortho is 1,2, meta is 1,3, para is 1,4. So what's going to happen? Well, alkyl groups are weakly activated. So both of these groups are weak. So they have about the same strength. Therefore, one product is not going to dominate over the other. Instead, for the most part, we're going to get a mixture of products. So these two products will roughly be equal. Now, granted, you might say one product is slightly more than the other because the ethyl group is more sterically hindered than the methyl group, so that might favor this product slightly more over the other, but nevertheless, if we get 52% and 48%, we could say that's roughly almost the same. So one product might slightly exceed the other, but for the most part, for all practical purposes, we're going to say that we're going to get a good mixture of both products. So these are the two products that we're going to get in this reaction in good yield. Now, what about this example? So once again, we're going to have two groups competing with each other. And the two groups will be a tert-butyl group and a methyl group. And let's react with Cl2 and iron 3 chloride. So what is the major product in this example? And what is the minor product? So once again, we have two alkyl groups. The tert-butyl group wants the chlorine atom to go in the ortho position, and the methyl group wants it to go in the ortho position with respect to itself. And so we can get two products. However, this time, it's not going to be equal. One product will clearly dominate over the other product. So the chlorine atom can go here, or it can go in the other position. We're going to draw both products. Now, which of these two products do you think is the major product? So when analyzing a reaction like this, you need to consider two things: directing effects and steric effects. So looking at directing effects, both the tert-butyl group and the methyl group, they're weakly activated. And so one doesn't favor the other in terms of directing effects. However, in terms of steric effects, this position is less accessible because of this bulky tert-butyl group. So it's hard for the electrophile to approach that position. This position is more accessible. And so as a result, it's easier for the electrophile to go there. And that's why this is going to be the major product. The chlorine atom is going to go on the most accessible position, assuming that these two groups have the same directing strength. And this is going to be the minor product because it's more difficult for the chlorine atom to approach the bulky tert-butyl group. And so make sure you take into account steric effects as well as directing effects. In the next example, we're going to have two alkyl groups attached to the benzene ring. But this time, the two alkyl groups, they won't be para with respect to each other. Instead, they're meta with respect to each other. And so let's react this with, let's use Br2 and FeBr3. So go ahead and predict the major product in this reaction. So here we have an isopropyl group and a methyl group. So both of these two groups are weakly activated. So they have the same strength in terms of directing effects. So we need to consider steric effects. Now, the isopropyl group, it wants to put the bromine atom in the ortho position. So notice that these two ortho positions, they're different from each other. And also, the isopropyl group wants to put the bromine atom in a para position. Now, the methyl group also wants to put the Br in the ortho position, which are those positions highlighted in green, and in the para position. So in this case, these two R groups, they're working together. They're not competing with each other. So we have three places in which we can put the bromine atom: position A, position B, and position C. Which position is most accessible? Position A is most accessible. Position C is the worst because it's between two alkyl groups. B is next to a bulky group, but it's not between two alkyl groups, so B is better than C. So position A will lead to the major product, B will lead to the minor product, and for the most part, this is so insignificant that it's usually not observed. So we're not going to include this product because the yield will be so low. So let's draw each product that we're going to get. So here's the first product with the bromine atom on position A. And as we said before, this is going to be the major product. And then the minor product, where the bromine atom is at position B. And so these are going to be the two main products in this reaction. But this is the major product because the bromine atom approached the ring at the most accessible position. Now sometimes you may get a question where you have two benzene rings as opposed to one, like this one. This is a typical exam problem. And let's react this with Br2 using the Lewis acid catalyst FeBr3. So what products will we get in this reaction? And if we do get multiple products, which one is going to be the major product? So feel free to pause the video and try this example. So the first thing we need to determine is which ring is the benzene going to go on? Is it going to go on the ring on the left side or on the ring at the right side? Which ring is more activated towards electrophilic aromatic substitution reactions? In an EAS reaction, bromine behaves as an electrophile. So you can represent it as E+, which means that the ring that is most nucleophilic is the one that is going to react with the electrophile. So which ring is most nucleophilic? So here we have a carbonyl group, and here we have an oxygen with two lone pairs. Which of these groups will make a ring more nucleophilic? Well, we need to draw resonance structures to find out. So let's focus on the carbonyl group. The carbonyl group is an electron withdrawing group. It can pull electrons from the ring by means of the resonance effect. Initially, this oxygen had two lone pairs. Now it has three. And so we have a double bond here and here. So notice that the carbonyl group can put a positive charge on the ring. So this ring is electrophilic and not nucleophilic. Two positive charges will not want to react with each other. In fact, they will repel. So we know that the bromine atom is not going to go on the left because that ring is electrophilic. The ring on the right, however, is nucleophilic. So notice that the oxygen with the lone pair can put a negative charge on that ring. So notice that we have a negative charge on the the ortho carbon, which means that the bromine atom can go on the ortho position, which means this is an ortho pair director. So right now the oxygen has one lone pair and a positive formal charge. Now we can take this lone pair, form a double bond, and push a negative charge on a paracarbon. And so this explains why the oxygen atom with the lone pair is an ortho pair director. As we can see, the ortho and the paracarbons, they're nucleophilic. Now we can't put a negative charge on the metacarbon, so the bromine atom is not going to go on the meta position. It's going to react with the most nucleophilic carbons because the bromine atom will behave as an electrophile in this reaction. So now that we know where it's going to go, we can draw the products of this reaction. So the bromine atom can go in a para position or in the ortho position. Now these two are the same, so I'm going to pick this one. Now, while I'm drawing these two products, I want you to think about which of these two products might be the major product. Should we put the bromine atom in the ortho position or in the para position? So make sure to take into account the steric effects. Now keep in mind, you can get both products in a decent yield, but one product is going to be better than the other one. And I'm pretty sure you know the answer based on the previous examples. It turns out that this one is going to be the major product because the para position is more accessible. I mean, this is not that bulky, but it's pretty much a big group, and so it takes up space, which makes the orthocarbon less accessible. So we can still get this product, but relative to the first one, this is going to be the minor product due to this relatively bulky group. So sometimes on a test, you might have to pick one of these two products, and both of them could be there. If you have to choose, I would go with this product, the one where the bromine atom is in the para position. Now let's move on to our next example. So starting with benzene, let's react it with butyl chloride and aluminum chloride. What's going to be the major product in this reaction? Now this is the Friedel-Crafts alkylation reaction, and you might be thinking, well, all we need to do is replace a hydrogen with the alkyl group. And for the most part, that's going to work out. I'm going to replace this hydrogen though. So is this the major product in this reaction? Granted, we could get this product, however, it's not going to be the major product. It's the minor product. In fact, the Friedel-Crafts alkylation reaction is subjected to carbocation rearrangements. Notice that the chlorine atom is on a primary carbon, and there's a higher substituted carbon next to it. So the benzene ring is going to go on the more substituted carbon. The major product is going to be this, where the benzene ring is attached to this carbon. So if we attach it here, we have an ethyl on the left and a methyl on the right after you kick out the Cl group. So the major product will look like this. So this is the answer you should put on a test. Now we definitely need to go over the mechanism for this reaction so you can see how it rearranges. So the first thing that's going to happen is the alkyl chloride is going to react with the Lewis acid catalyst. And so we're going to get an intermediate that looks like this. When aluminum has 4 bonds, it's going to have a negative formal charge. And when chlorine has 2 bonds, it has a positive formal charge in 2 lone pairs. Now, if we kick out the chlorine group right now, we're going to get an unstable primary carbocation, which we could do at hydride shift to get a more stable secondary carbocation. And this is the species that's going to react with the benzene ring. This is the electrophile, our E+ reactant. However, the only issue with this is that primary carbocations are very high in potential energy, and so they're very difficult to form. So let's find a way to avoid the formation of an unstable primary carbocation intermediate. And what we can do is we can do a hydride shift at the same time we kick out the chlorine leaving group. So this hydrogen is going to move to that carbon, causing the carbon-chlorine bond to break. Because chlorine is more electronegative than carbon, when the CCl bond breaks, the electrons will go towards the chlorine atom. And so by doing this, we can avoid the formation of an unstable primary carbocation intermediate, jumping directly to the secondary carbocation. By the way, I want to mention that if you need the mechanisms for the other reactions, such as the nitration of benzene or the sulfonation of benzene, you could find all of my videos in my new organic chemistry playlist, which is in the description section of this video. So feel free to take a look at that. Now let's continue with this reaction. So here is the benzene ring. And keep in mind, we're dealing with an electrophilic aromatic substitution reaction. So it's a substitution reaction, which means we're going to substitute the hydrogen with this group. And we're substituting it with an electrophile. And we're dealing with an aromatic ring. So that's why it's called an electrophilic aromatic substitution reaction. So the first thing that's going to happen, let me redraw this. The benzene ring is going to attack the carbocation. So I'm going to add the alkyl group to this carbon, and plus charge will be on this carbon now. Notice that we went from a stable aromatic ring to an unstable intermediate. Therefore, this hydrogen is very acidic. It wants to leave so that the benzene ring, or this intermediate, can reform the aromatic ring. So we need a base. So I'm going to use a generic base, which could be AlCl4-. It could be the chloride, or it could be the solvent. So that base is going to go for the hydrogen. The carbon-hydrogen bond is going to break, regenerating the aromatic ring. And so this is going to be the final product in this reaction. Now for the next example, we're going to start with nitrobenzene. What's going to happen if we react nitrobenzene with tert-butyl chloride and AlCl3? So what's the major product of this reaction? Now, we know that the NO2 group is a meta-director. So you might be thinking, well, hey, this should be the product. Now, this is not going to rearrange because the chlorine atom is on a tertiary carbon, which is more substituted than the 3 primary carbons around it. So are we going to get this product in this reaction? Or is there something else that we need to know about this reaction? This is the Friedel-Crafts alkylation reaction, and it does not work if you have a strongly deactivating group like an NO2 group. So we're not going to get this product. So no reaction for this. There's 3 limitations of the Friedel-Crafts alkylation reaction that you need to be aware of. The first one, let's start with benzene. And let's react benzene with methyl chloride and AlCl3. So this is going to give us toluene as the monoalkylated product. Now, the R group is a weakly activating group, so therefore toluene is more nucleophilic and more reactive than benzene. So therefore, this is more likely to react with another methyl chloride than benzene. So this is going to react again. Now the second methyl group can go in the ortho position or in the para position. So I'm going to just pick one of these two and put it in the para position. Now it doesn't stop here, because this is even more reactive than methylbenzene or toluene. And so another methyl group can be added to this ring. And so this is one of the disadvantages or the limitations of the Friedel-Crafts alkylation reaction, is that polyalkylations can occur. So if you start with benzene, you're not just going to get one R group, but you may get 2 R groups or 3 R groups and even more than that. So that's one limitation you need to be aware of. The other 2 we talked about already, and that is carbocation rearrangements can occur with the Friedel-Crafts alkylation. When we tried to react benzene with butyl chloride, we got a sec-butyl group instead of a butyl benzene. So that's the second limitation, carbocation rearrangements. The third is that you can't use the Friedel-Crafts alkylation reaction if you have a strongly deactivated ring. So we saw that when we had nitrobenzene, it wouldn't work with the Friedel-Crafts alkylation reaction because that ring was strongly deactivated. So make sure you know those 3 limitations for the Friedel-Crafts alkylation reaction. Now let's work on some synthesis problems. So starting with benzene, how can we make benzoic acid? What reagents do we need to convert benzene into benzoic acid? Feel free to pause the video and try that problem. For each question after this one, make sure to pause the video, work out the problem, and see if you can get the answer. So let's begin. The first thing we need to do is we need to react this with, we could use ethyl chloride and AlCl3. So the Friedel-Crafts alkylation reaction. And in order to get the monoalkylated product, or at least to increase the yield of the monoalkylated product, what we need to do is basically use excess benzene and a small amount of ethyl chloride so that we can decrease the chances of a benzene molecule with an ethyl group reacting a second time. So that can increase the yield of the monoalkylated product, reducing the yields of the polyalkylated product. So we need to use excess benzene. Now, once we have the first R group, we need to oxidize the ethyl group. It's known as a side chain reaction or side chain oxidation. One reagent that we can do, or we could use rather, is chromic acid with heat. So what's going to happen is it's going to convert this group into a carboxylic acid. Every carbon except the first carbon will be cleaved. And so this is going to turn into benzoic acid, which we can draw like this if we want to. And so that's how we can convert benzene into benzoic acid. Now, let's convert benzene into aniline. So what reagents do we need in order to put an NH2 group on a ring? Now keep in mind there's multiple ways in which to do this, but I'm going to focus on the electrophilic aromatic substitution reactions that will lead to this product. One simple way is first to use nitration, nitric acid and sulfuric acid. And so this will replace a hydrogen with the nitro group. And then the second thing that we could do is reduce the NO2 group into the NH2 group. And so by using a metal like iron metal or zinc metal, the NO2 group will convert to the NH2 group. And so these are the two reagents that we need. Another way in which you can do this, which is in the section nucleophilic aromatic substitution reactions, is to react the ring with a bromine atom, let's say Br2 and FeBr3. So once you put a bromine atom on a ring, then you need to use sodium amide. The net effect is that the bromine atom will be replaced with an NH2 group. Now, if you want to look up this reaction, in your textbook, under the section nucleophilic aromatic substitution reactions, look for something called benzyne intermediate, because that's how bromobenzene is converted to aniline. It's through the benzyne intermediate. So feel free to take a look at that. That's another way in which you can convert benzene into aniline. Now for the next example, we're going to convert benzene into benzaldehyde. So how can we do this? What's a simple way in which we can put an aldehyde functional group on a benzene ring? Now there's a reaction that's called the Gattermann-Koch reaction. Basically, you're using carbon monoxide with hydrochloric acid and aluminum chloride and copper chloride. It works in a similar way to the Friedel-Crafts acetylation reaction. These two, they will make an acid chloride, an unstable acid chloride called formyl chloride, and then this will react with this catalyst and that one too to basically put an aldehyde functional group. The chlorine atom is going to leave. And so that's the basic idea behind the Gattermann-Koch reaction. So that's how you can convert benzene into benzaldehyde. Now, starting from benzene, how can we make propylbenzene? So go ahead and try that. Now, if you're thinking of using butyl chloride with aluminum chloride, this is not going to work. You won't get this product in good yield. Keep in mind, this is a Friedel-Crafts alkylation reaction, and it's subject to rearrangements. A hydride shift will occur so that the benzene ring doesn't attack the primary carbon, but instead attacks a secondary carbocation. So if we use propyl chloride, the major product will be isopropylbenzene rather than propylbenzene. So therefore, we need to do something else. What we need instead is we need to use the Friedel-Crafts acylation reaction. So we need to use an acid chloride with aluminum chloride. So that's the first step. And what's going to happen is we're going to replace a hydrogen atom with an acyl group. And so we're going to get a ketone. Now, this ketone will complex with the aluminum chloride catalyst, and we're going to get something like this at the end of this reaction. So to get rid of this catalyst, we need to add water. So water is going to get rid of the aluminum atom from bonding to the oxygen. And so that's going to give us the ketone. The last step, so this is step number 1, this is step 2. The third step is to reduce the ketone to an alkane. And so we can use the Clemmensen reduction where we have amalgamated zinc, so basically zinc and mercury alloyed together under acidic conditions. And that's going to basically replace the carbonyl group with 2 hydrogen atoms. So that's how we can convert benzene into propylbenzene. Now for our next example, how can we convert bromobenzene into toluene? So how can we replace the bromine atom that's already on the benzene ring with a methyl group? One way in which we can do this is using the Gilman reagent, also known as the organocuprate reagent. And so we need dimethyl copper lithium. And what's going to happen is one of the R groups, in this case a methyl group, is simply going to replace the bromine atom. And so this is just one of those reactions that you need to know. Now let's talk about how we could synthesize a disubstituted benzene derivative. So in this case, we want 2 substituents that are meta with respect to each other. One is going to be a sulfonic acid and the other an iodine atom. So how can we make this compound from benzene? The first thing we need to talk about is which group should we add first. Now let's say if we decide to perform iodination first. So the first group, we can put it anywhere. So I'm just going to put it at the top. Now, iodine is an orthopair director. So once we react this with concentrated sulfuric acid, and once we heat it, the SO3H group will go in the ortho position or in the pair position, but it won't go in a meta position. So the order in which we use the reagents matter. So we don't want to use iodine in the first step. Rather, in the first step, we want to use concentrated sulfuric acid with heat. So we can place that group anywhere. So we're going to put it here. And then the sulfonic acid group is a strong deactivating group, and it's also a meta director. So once we react this with I2 and nitric acid, the iodine atom is going to go here, which is going to give us this product. And so that's how we can make it. In the first step, we need to use concentrated sulfuric acid with heat, and then in the second step, iodination. Now, in the next example, let's talk about how we can convert benzene into para-nitrobenzoic acid. So how can we make this compound? What reagents do we need? So looking at the product, the two substituents are para with respect to each other. Now, the NO2 group is a meta-director, and the carboxylic acid group is also a meta-director. So if both of these two groups are meta-directed, how can we place them para to each other? So when you get a situation like this, you need to look for the intermediate. There must be an intermediate that is an ortho-para director. And if you recall, earlier in this video, we talked about how to synthesize a benzoic acid. And first, we need to add an alkyl group and then oxidize it to a carboxylic acid. Now, the alkyl group is an ortho-para director. So what type of alkyl group do we want to add? If we add a methyl group, we're going to get a mixture of products. We're going to get the ortho product and the para product. So what can we do to increase the yield of the para product over the ortho product? Well, the answer is to use a bulkier group. Now, if we use tert-butyl, notice that tert-butyl is, this carbon here is a quaternary carbon. It has no benzylic hydrogen atoms, so it's resistant to oxidation. If you try to react it with chromic acid and heat, nothing's going to happen. It's not going to turn into a carboxylic acid. And so tert-butyl groups are resistant to oxidation. So the next best thing is to replace it with an isopropyl group. At least we have one benzylic hydrogen, so it can be oxidized into a carboxylic acid. So in the first step, we're going to use the Friedel-Crafts alkylation reaction with isopropyl chloride and aluminum chloride. And so that's going to give us this group. And then we can perform nitration. So using nitric acid and sulfuric acid, the para product will be favored over the ortho product. We can still get both, but the major product will be the para product, since the isopropyl group is a relatively bulky group. So now that we have our two groups in the right position, the last thing we need to do is oxidize the isopropyl group. So you can use chromic acid with heat, or let's use something different. This is going to be step 1. This is step 2. In step 3, we could use potassium permanganate with hydroxide under high temperature conditions. So that's going to give us a deprotonated carboxylic acid group. So to get it protonated in the fourth step, we need to acidify the solution. We don't want benzoate, we want benzoic acid with the NO2 group. So we need to use H3O plus in the fourth step. And so that's how we can make para-nitrobenzoic acid. Now for the next example, starting with benzene, let's make metachloroaniline. So go ahead and try this example. How can we make this product? So the first thing we need to realize is that the two substituents are meta with respect to each other. And chlorine is an ortho-para director, and H2 is an ortho-para director. So therefore, we need some intermediate that's meta-directed. In order to make the NH2 group, we need to make the NO2 group first. And that's a meta-director. So that should be the first reaction that we should be dealing with. So that is the nitration of benzene. And so this is going to give us nitrobenzene. Now we don't want to reduce NO2 to NH2 yet, because this will convert to an ortho-para director. So at this point, we want to add a chlorine with AlCl3. And so the NO2 will direct the chlorine to the meta position, which is where we want it. So now, at this point, we can reduce the NO2 group to the NH2 group. So the final step, that is the third step, we can use a metal like zinc and hydrochloric acid. You could also use tin and hydrochloric acid. So there's a lot of reducing agents that you could use here. Even hydrogen gas will work with palladium over carbon. So any one of these reducing agents will convert the NO2 group to the NH2 group. Now, in the next problem, let's convert benzene into para-nitroaniline. So what do you think we need to do in this example? Feel free to pause the video. So NO2 is a meta director, and these two are para with respect to each other, so we don't want to put the NO2 group first. We want to get the NH2 group and then put the NO2 group, because the NH2 group is an orthopara director. So this implies that we need to nitrate the ring first in order to even get to the NH2. I'm going to put it here. So this is the NO2 group. Now once we have nitrobenzene, the next step is to reduce it with a metal and an acid. So the NO2 group will be converted to NH2. Now what's our next step? Should we react this with another nitric acid? So by the way, this is the first step and this is the second step. So let's start with aniline. How can we place the NO2 group at the para position? Can we react aniline with nitric acid and sulfuric acid? In this case, this is not going to work. The NH2 group is easily oxidized, and so you can get a lot of different stuff here. So you shouldn't use nitration with aniline. Second, under acidic conditions, the NH2 group can easily be protonated. And once that happens, this is no longer an orthopara director because it can't donate electron density to the ring using its lone pair since the lone pair is gone. So all it can do is withdraw electron density from the ring, making it a meta director. And so using aniline under acidic conditions is not going to give us the orthopara effect that we want. So we need to do something else. What do you think we need to do here? In a situation like this, we need to protect the NH2 group. And we can do so by converting it into an amide. So I'm going to use an acid chloride to do so. And what's going to happen is we're going to lose a hydrogen and a chlorine atom. And so it's going to leave as HCl. That's going to be our side product. And whenever you mix an amine with an acid chloride, you're going to get an amide. Now the amide is not as strongly activating as an amine on a benzene ring. However, it's moderately activating, but it's still orthopara directing, which is what we want. So now we can use the amide with nitration. It'll work, but we can't use nitration on aniline or with an amine group on a benzene ring. That's not going to work. So we do have a lone pair on the NH group, so it can donate electron density to the ring. So we could put a lone pair on the orthocarbon, or we could put a lone pair on the paracarbon. So we can see that it's still orthopara directing. Now we do have a bulky group, and the bulky group will, okay, what just happened there? The bulky group here will reduce the ortho yield, favoring the para product. So that's why I added this tert-butyl group at the end, so that we can get a better yield of the para product over the ortho product. And so right now, we're going to get this product. Now the last thing that we need to do is we need to get rid of the amide functional group, turning it back into an NH2 group. So how can we do that? What we need to do is react our product with hydrochloric acid in water and with heat. When you put these two together equivalently, this is the same as H3O plus with heat. And so what's going to happen is the amide bond is going to break. This part will turn into a carboxylic acid, and this part will turn into a protonated amine. And so after reacting it with H3O plus and heat, we're going to get the NH3 plus group, and we're also going to get, well, the nitro group is going to stay here, so there's nothing new there. And then the acid chloride is now a carboxylic acid. The last thing we need to do is add hydroxide. So that's the final step. Hydroxide will deprotonate the NH3 group, giving us the product that we want. It will also get rid of the hydrogen on the carboxylic acid. And so this is going to give us para-nitroaniline. And as a side product, a carboxylate ion. But this is the product that we want. And so that's how we can make it. Now let's move on to the next situation. So we're going to start with tert-butylbenzene. And the goal is to put a bromine atom on the benzene ring, but in the ortho position. So how can we do this? Well, you might be thinking to use Br2 and FeBr3. And so that could give us this product. The only issue is we're not going to get it in good yield. The tert-butyl group is an alkyl group, so it's orthoparadirectin. However, this position is not as accessible as this position. So the major product will be the para product. So how can we increase the yield of the ortho product and avoid getting the para product? What do you think we can do here? Because if we use Br2 with FeBr3, we're not going to get this product in good yield. So what we need to do is we need to use a blocking group, something that will block this position. And it has to be removable too. The best thing we could do is use sulfuric acid, concentrated sulfuric acid, with heat. And so what's going to happen is it's not going to go here because it's not accessible. At least that will be a minor product, but the major product will be adding the SO3H group to the para position because of this bulky tert-butyl group. And so after this step, for the most part, the majority of the product will be in this form. Our next step will be to react it with Br2 and iron 3 bromide. The tert-butyl group is an orthoparadirector, but the para position is occupied, so it's not going to go there, even though that's the favorable position. So the tert-butyl group can only direct the bromine atom in the ortho position. Now, sulfonic acid is a meta-director, so it's going to direct the bromine atom in the meta position. So in this case, both groups are working together to put the bromine atom here. And so we're going to get this product in good yield, even though it's not very accessible there due to the bulky tert-butyl group. However, it's the only place it can go. And so that's how we can get the ortho product in good yield. But we're not finished yet. The last thing we need to do is we need to remove the blocking group. So basically, we need to perform a desulfonation reaction. And so you need to add water with acid or simply H3O plus. And you also need to heat the solution. When you heat it, this will leave as sulfur trioxide. And sulfur trioxide, it has a boiling point of around 45 degrees Celsius. So once you heat it, it will escape as a gas, thus driving the reaction forward. Because this reaction is reversible, but when you heat it, the decreased concentration of the product, according to Le Chatelier's principle, whenever you decrease the concentration of a product, the reaction will shift to the right to make more product so that it can maintain a state of equilibrium. So as the gas escapes the reaction vessel, the system will shift to the right, favoring desulfonation over sulfonation. And basically, we're going to get rid of the sulfonic acid group, giving us our final product, which only contains the tert-butyl group and the bromine atom ortho with respect to each other. And so that's how we can make it. So thus you can see the advantage of using a blocking group. You can use sulfonic acid to block a position, and then once you add your group, you can then desulfonate the ring, removing the blocking group, giving you your product. Now there's one more example that I want to go over. So let's make a tri-substituted product. So starting from benzene, how can we put these three groups in these positions? So we want to add a tert-butyl group, a bromine atom, and a nitro group. So what is the order in which we should add these three groups? So let's pick one. Let's start by adding the NO2 group. If we add the NO2 group first, we know that it's a meta director. So the next thing that makes sense to do is to add the bromine atom. So the NO2 group will put the bromine atom in the meta position. Now, the bromine atom will want the tert-butyl group to go in the ortho and the para position. The NO2 group wants the tert-butyl group to go here. Now, bromine is weakly deactivating, NO2 is strongly deactivating, so bromine is more activating than NO2, so bromine's going to win. Now, we could get this product, which is the product that we want, but we can also get this product too. So we're going to get this product plus another example. So we'll get this other product as, not that one. I meant to put the tert-butyl group here. So these are the two products that we would get if we chose to add NO2 first, then Br, and then the tert-butyl group. Now, let's assume that these two products are equal. So the product that we want, we would get it in a 50% yield, which is not bad. But let's see if there's a way in which we can get a better yield than 50%. So if you chose to put NO2 first, then Br, and then the tert-butyl group, you would not be wrong. You would get the product that you want, but it may not be in the best yield. Now let's add the bromine atom first. Let's see what's going to happen. Now if we add the bromine atom, we don't want to add the NO2 group yet because bromine is an ortho-para director. So the next thing that we should do is add the tert-butyl group. Bromine can direct it here or here. So right then and there we can get a mixture of products. We can get this one and we can get this one. However, this product seems to be more favorable with the tert-butyl group being away from the bromine atom since it's so bulky. So right now, this situation doesn't look good. But let's continue. Now, if we add NO2 to this ring, the tert-butyl group wants it to go in the ortho and in the para position. Bromine wants the NO2 group to go to the ortho or the para position. And so these two are competing with each other, but the tert-butyl group is weakly activating, the bromine group is weakly deactivating, so we could get the NO2 group here because it's going to be hard for the NO2 group to go there because of the bulky tert-butyl group. So this could work. However, we're competing this product with this one. So at best, to get this product, it's not going to be any more than 50%. Automatically, there's no point looking at this because the bromine atom and the tert-butyl group, they're not in the right position. So let's see what happens if we add the tert-butyl group first. So if we put the tert-butyl group first, we know that it's an ortho and it's a para-directing group. So we don't want to put the bromine atom right now because para is more favorable than ortho when dealing with tert-butyl. So the next thing to do is to put the NO2 group because it's easier to put the NO2 group here than here. This is the more accessible position. So we're going to get this product in good yield, not in a 50-50% yield, but more like an 80-20 or 90-10 yield. Now the tert-butyl group has no choice but to put the next group in the ortho position. It can do so here, but those two are the same. Now the NO2 group is a meta-directing group, so it can direct the Br to the same position. Therefore, we can get this product in good yield. So now that we know the order in which to put these three groups on a ring, let's write out what we need. So the first step is to use tert-butyl chloride with aluminum chloride. So that's going to be the Friedel-Crafts alkylation reaction. And then the second step is nitration. Nitric acid with sulfuric acid. And then the final step is bromination using Br2 and the FeBr3 Lewis acid catalyst. And so in this order, we can get the best yield for this product. We won't get competing products, but we're just going to get one major product. And so sometimes there's a way to get the ideal product that you want in a better yield than other methods. So the order in which you react the benzene ring with these reagents matters.